Okay, so find the phase planes. Okay, let's just start with a linear example. There are some different versions of phase planes. Sometimes, rarely, you plot rates versus states. The rate of a variable versus the state variable. That's also called, those are also called phase plots. But we are going to discuss first, by and large, the most typical definition of phase plot, which is one state versus the other. That's the most typical usage. But as I said, you may also have the rate of a state versus the state itself. That also would be called a phase plot, a kind of phase plot. That type of phase plot, rate versus state, would be used, for instance, in first order systems. If you want to analyze a first order system, linear or nonlinear, then you don't have two state variables, so you plot one rate of the state versus the state variable. But here you see the most typical example, state versus state plot. So here, let us take a linear system. A linear model, which is well, let us say this is dx over dt equals x plus y, dy over dt equals minus 4x plus y. This is homogeneous. Which would be always be assumed. Okay, now this statement, we'll come back to this later, but now let me just quickly say, this is a homogeneous system, right? If it's not homogeneous, we will assume it's homogeneous. We will forget about again, once again, just like equilibrium and stability analysis, we will ignore non-homogeneous component, because again, the fundamental purpose of a phase analysis, phase plot, phase planes, is to understand the endogenous internal systemic dynamics of a system, stability or equilibrium point, rather than the cause of the input function, the result of the input function. That's one reason. The other reason is, by some transformation, again, as we'll also see, you can always put a non-homogeneous system into a homogeneous form anyway, by transformation of variables. So that's one more reason. And yet, a third reason why you don't use the non-homogeneous component is the interpretation. If you do it with a non-homogeneous function, it becomes exceedingly difficult. It just becomes too difficult, as I'll explain again later. Right? So there are several reasons. There is not much value in analyzing the non-homogeneous component. It makes the interpretation of the graph too hard, and we are interested in the stability of the system and the dynamics around the equilibrium points anyway. So for that reason, homogeneous component is enough. For all these reasons, typically, you either have in this form or you bring it in this form, in homogeneous form. Huh? You can still ignore it. You can still ignore it, of course. Then the dynamics that you will get will not be the same as the dynamics of the non-homogeneous. But once again, if the non-homogeneous component is a stable function, then the dynamics, the long-term dynamics, will be what you will be obtaining. All right, the long term. The long-term trajectory will be what, because in the long term that will be gone. Okay, it will be negligible or near zero if it's a stable function. Okay, if it goes to zero, that means the long-term dynamics will be what you are obtaining anyway. So when you plot the phase trajectories, if you are really after the long-term trajectories, it's not unsafe to ignore the time input. Now, if the time input is unstable, then it becomes a whole different business. Then it's difficult. By ignoring, you are going to get errors. But then again, it doesn't become an interesting stability problem anyway, because then that non-homogeneous component in the long term will completely dominate the system. So we may come back to that later. Well, okay, here are some steps. The first, basically, most of the steps that of a phase plane are the tools and the kind of things that you already learned, you just put them together. One is find equilibrium point. The first step is find equilibrium point. And in this system, without doing much work, you know that the equilibrium point will be what? It's a linear, homogeneous system. It's zero. So the equilibrium points are x, y equals 0, 0. In this case. 2, stability. All right. Now, for stability, we are going to analyze the eigenvalues, right? If it's linear, you just immediately write down the eigenvalues. Eigenvalue equation. If it's not linear, then you first what? So, if linear, proceed directly with eigenvalues. If it's not linear, then what? Huh? Around each equilibrium, it's not linear, right? Around each equilibrium. All right. So since this is linear, here I am just going to give you the lambda, the eigenvalue equation is minus lambda square minus 2 lambda plus 5 equals 0. If you do this, you get that. So this is equal to 2 plus or minus square root of what? 4 minus 20 divided by 2. Okay. So what do you get? What are these? 1 plus or minus 5. Okay, so what's your conclusion about stability? What is it? Unstable. The equilibrium point is unstable and the system is globally unstable, right? And then what do you do? The third step is, well, the third step, we haven't discussed yet. The third step is you write what's called phase equation, all right? Right? Phase equation. The phase equations are dy over dx or dx over dx. The rate of change of a state versus the other one. And you can do that by taking, by actually dividing the two. Alright? So dy over dx then will be from here minus 4x plus y divided by x plus y. Alright? So that's called a phase equation. Alright? The rate of the change of x with respect to change of y. Alright? From here, you find what are called isoclines. Okay? Or you may have some, what other names do you know about? One name of this is called isoclines, or sometimes called nullclines. Okay? Nullclines, isoclines. Did you learn some words for these? So, find, using this, find isocline. You know, iso means equal, right? Iso. Clines are slopes. Equal slope contours. Okay? You find equal slope contours from this. So the very equal slope contour, for instance, examples are dy over dx equals 0. If you equate this 0, you wonder what kind of equations you get. So this is on this when this condition is satisfied, meaning y equals 4x. So this is called zero isoclines. So these are like zero sort of slope contours. Whenever the solutions are on this line, they should have a slope of what? Dy over dx slope should be what? 0. No, not 4. This is tricky. Okay? This is not the, when you write this condition, you get this equation. This is the result of that. So this is tricky. Yeah. That's you know, the slope of this is not the dy over dx slope. So when you put it, you see what I mean. This is the result of this condition. Similarly, dy over dx. Here's another famous isocline. Some isoclines are famous. Approaches infinity. You know, the horizontal and vertical are what? Are essential ones. You need to do these two. So that approaches infinity on what? Huh? Yeah, plus y equals 0 from here, y equals minus h. So these are the two isoclines. Now you can find more isoclines, which I put in parentheses, I'm not doing it now. For instance, you can find an isocline of 1, right? The isocline of 1 says what? This is equal 1, right? I'm sorry, this is equal 1. So you can solve that and see what you get. All right? İkişer yapacağım. Tabii bir tane bir üstünlüğü ki ikişer yapacak. So you could do similarly. You typically do this and perhaps plus 1 and perhaps not too many. You know, 1 minus 1 and at most maybe 2 minus 2 and perhaps half. But you don't do too many of these by hand. Now the computer will do what? You know, all the kind of span all the space will do, you know 1/4, 1/2, 1 1/4, whatever. It just goes like this and all the negatives so that it can give you a numeric impression of the phase plane. But let's just now proceed and see what we have. We can talk about this. The fourth one then is the last step. What we say is determine the field or direction arrow. Determine field or direction, field arrows or direction arrows, and plot phase trajectory. This is the phase trajectory. So this is the final phase. So let us say this is Y, this is X. Now we are going to put everything together. What do we have? The equilibrium point. Where is the equilibrium point? Here. Alright, this is the equilibrium point, 0, 0. Right? You mark the equilibrium point. Here we only have one. 2, you know about the stability, we'll use this information later. 2, you plot the isoclines. One is y equals minus x is this line. No, is this line, right? And y equals 4x is this line. So let us say this is y equals 4x, right? Something like that. So this is y equals 4x. I don't know, it may be correct. Okay? This is y equals 4x line. The other one is y equals minus x in this. Assume this is going through this and it has the right slope. So this is y equals minus x. Now coming back to your question, you see, we are saying that we are going to plot some trajectory. Now remember, y versus x is not a function. Y is changing over time, x is changing over time, so that y versus x is sort of like a correlogram. It's like a correlation flow. How are the two changed together so that's not necessarily a function? Alright? So for that reason, all we are finding from here is when they happen to be, when they cross this, they cross with a slope of what? 0. You see? So that's why you show something like this. This is the 0 slope. Alright? That's a piece of information for you. That's something that's not to be violated. Okay? And the other one, here, this line, they cross with the slope of what? Infinity. Okay. Now we could do more. If you want, you can immediately do. You can do 1, right? Ha? Hangisini? Şunlara bak. This is an infinite slope, right? So when I am plotting a y versus x motion, when y and x move together, dy over dx, as they pass through here, must have a slope of infinity. This indicates an infinite slope. Why? Because I found it that way. I equated dy over dx to infinity. Then you would have, you took multiply, then you took multiply. Let us say that equation was something like this. I'm just making this up. Something like this, correct? Then you put multiply this one. Because these are the one slopes of one. Huh? Huh? Yeah, you put 45 degree line there. You didn't do that. Okay? Alright? Okay? So, now, we will now plot the phase trajectory. Oh, no, I'm sorry. We will do the field or direction arrows. Okay? Now, here is what you do. You come over here. You say, as it turns out, these trajectories, these isoclines, this is an isocline, and this is an isocline. The isoclines are also lines that separate the regions in which, this is important, y increases or decreases, and x increases or decreases, vice versa. Why? Because if you think about it, for instance, one of the isocline is when this is equal to 0, and the other isocline is when this is equal to 0. Do you see? What does it mean? When this is equal to 0, take this one. When this is equal to 0, y is not changing. Do you agree? And when you are on the other side of the line, you are greater than this line, then this becomes what? dy over dt becomes what? Positive. So y increases. And when dy over dt is negative, then y decreases. Okay? So this line, the line that actually separates the region where y decreases versus y increases. What is that line? This line is which one? This line, right? So when you are on this side, I have y goes down, all right? When y is below that line, so when y is below this line. Because then what? When y is below this, the whole thing becomes negative. Do you see that? So when y is below this line, y is, so all in this region, y does what? Y goes down. Do you agree? It doesn't matter whether you are here, whether negative, positive, you are still here, and whether you are here. It's all the same rule. So you put the arrows like this. And you are on this side, what happens is what? Whether you are here, or you are here, or you are here, do you agree? Or you are here. So the two regions. Okay? You do the same for x, and the same goes for x. So when x is, well, this time, this is 0, when what happens is this is the line, right? Okay? For take some typical point. Well, when they are both positive, it's obvious that when you are on this line, then over here, what happens? X goes up. But it will also go up even if you are here. Do you agree? Mm-hmm. Why? Because, still, when you are here, which one is negative? X is negative, but y is larger in number, y is greater in number. So you can tell that the rule applies. When you are above this, you have what? X goes up. Okay? Right? Yeah, positive. X plus y becomes positive. So now you connect these with this. Okay? You can put them over here, but it's healthier if you put it like this. Because that's good, that's all. Right. Because what happens is these vectors show the possible direction of movement. So the movement will be somewhere in between, because you cannot violate this. You cannot go, when you have a point, you cannot go like this. Not violating these will be the movement should be not so as to not violate these arrows. The movement must be in between. That's why you connect the arrow to show it like that. And then down here you have x goes down, down goes down, down here goes down. This is the situation. So I have the field arrows. You can have many, more field arrows. When you do this by computer, you have more field arrows. So now what do? Now I try to use all this information, everything, including the stability, to plot phase trajectories. The way you plot the phase trajectories by hand, and the computer does by its own hand, you put your hand somewhere near the equilibrium points, near each equilibrium point, and you say, how will I move? What's the feasible and possible movement? And so you obey these rules, and you try to plot some trajectories that obey all these rules. So for instance, if you start here, what can you do? What will x and y? This is an x0, y0. Do you agree? This is an x0, y0. point. What will it do? If I start here, it will obey this. So which way will it move? Can it move like this, like this, like this, or it will go like this, right? It will go down, and when it comes down, it will continue this direction, which means somewhere like around the resultant of these vectors, right? In the direction, something like a resultant of these vectors. So if you move like this, then this is critical. When it comes down here, it will have a perfectly vertical motion. Then it will turn, right? So now we can do this. So you see, it goes to do something like this. Do you agree? Something like that. And then you put the arrows to show the direction of motion. It's not moving this way because you will forget otherwise. You do it by hand, but when you look statically, you don't see it. This is direct. The arrow shows what? How you advance on that path as time goes by. Remember, there is no time left here. Time is implicit. The third variable, time, is what? Is implicit. That's shown by the arrows. Okay? So you move like this, and then you turn around. Do you agree? Is this correct again? Am I obeying this? I'm not violating this. I'm not violating the isotope line. Seems to be okay. Now, so I go like this. Something like this, right? This is supposed to be like this. Right? Okay? So I go like that. Right? I'm still not violating it. Do you see? Do you agree? This is the motion, which doesn't violate any of the arrows, any of the isotope. Now you start another one, perhaps closer, because if you start another one from here, it doesn't try. If you start from here, then what does it do? It goes like this, and it goes up. So it's kind of like right? There's another exterior way to do it. You see? Now take a look at this one now. This is the new one. Okay? Now I will stop here. Huh? Huh? Yeah, I didn't violate any of the, but then I ended up. Now, these arrows seem to be okay. All I did was sort of, a careful geometric movement, so to speak, as time goes by, without violating any of the arrows. But I will also check to make sure that it's okay. I will go back to my stability condition. The stability condition says what? This point is what? Is unstable. And more precisely, what kind of unstable is it? What kind of movement does it have? In other words, do you have more information than just saying unstable? Or what type of unstable is it? Yeah. More precisely, it's an unstable oscillation. Right? An increasing, growing amplitude oscillation. So it's unstable, but the type of instability is one of increasing oscillation, growing amplitude oscillation. Well, let's do one more here. Take a look at this. One last one here. Because I start very closely now. So it goes like this. Now, once again, take a look at this. The last one. Be careful. The trajectory, see the last one I did? The last one I did was this. The last one I know is this one, right? And you see, do you see why I erased it? I erased the other one because I realized I crossed this one. There's a very important rule which goes all the way to the uniqueness of solutions of differential equations, one of the fundamental theorems of differential equations. Trajectories cannot cross each other. No trajectories can cross. Because if they cross, then you violate uniqueness condition theorem. Why? Because then if you start on that point, you don't know which way you will go. If they cross, then the proof is that's not possible. If you say, let us assume they cross and you start on the point, then it's against uniqueness because you don't know which way you will go. Will you go this way? Will you go this way? It's undefined. So that's why the uniqueness theorem says trajectories cannot cross. Phase trajectories cannot cross. So anyway, so you see this? Now what kind of, do you see what kind of movement is this? Is it indeed, does this growing oscillations, does it dictate this type of phase trajectory? You have a small h, small y, then you have a what? An increasing x in amplitude. You see x is increasing. X was small, then it's increasing in amplitude. It's going down, but it's increasing, right? X is going down and increasing in magnitude. You see? Then y is what here? Is going up and increasing in amplitude. Do you agree? X is sort of not growing anymore. In this region, what happens is what? Both x and y are growing what? In amplitude. After a while, y is decreasing in amplitude, x is growing in a positive direction in amplitude. Then after a while, y is growing in what? In negative amplitude, negative direction, and x is decreasing in amplitude. So if you plot this x and y, you will see that it corresponds to this sort of motion. One of them does something like this, and the other one with perhaps some sort of phase lag. There's a phase, some degree of phase lag, which is to be studied, of course. After some phase lag, perhaps the other one is over here, does perhaps does something like this. All right? See, both are, there's a phase lag in between. They don't do it at the same time. But both are what? Both exhibit growing oscillation, growing amplitude oscillation. So this picture corresponds to this type of time trajectory, which is taken away. Question? Okay? So these are called phase trajectories. That's the name. These are called phase trajectories. Why are phase trajectories important? Well, first of all, I didn't solve this. You see? I obtained a geometric interpretation, what's called sometimes a qualitative analysis, but I was able to almost deduce what? From here, the time trajectories, the dynamics or the solutions of the differential equations, which is a nice piece of information. When you look at the phase trajectories, you see the equilibrium, but in one shot you see what? The equilibrium points, the stability of each equilibrium point. More specifically, the nature of stability of the equilibrium point, the type of stability of these points. And finally, perhaps a way of what? Deduce approximately how the time trajectories will look like. Okay? Now, well, this is the idea. This is the summary of phase trajectories. Now, note that, as I said, let me write this note down immediately before we forget. A very important note. So at any point, there is at most one trajectory, or no trajectory can cross okay. You cannot have more than one trajectory through any point. Okay, that's what it says. Trajectory you cannot cross. And otherwise it would be against, as I say, it would be against uniqueness of solutions of differential equation. To give a deterministic differential equation, starting with a given initial condition, it will go, the uniqueness theorem says what? Whether you are able to find the solution or not, the uniqueness and existence of solution say what? There is a solution and it's unique. It has a behavior and it has a unique what? Behavior. You cannot have two different behaviors starting from 12 arbitrary behaviors in a service differential equation starting at the same initial condition. That's impossible. That's what it says. The two, also, a similar statement, again, the result of very similar statement. A given trajectory cannot cross itself, same thing. Same thing also. I mean, two different trajectories cannot cross, and you cannot have a single trajectory going and coming back and crossing itself for the same reason. These are true in, of course, once again, homogeneous systems. Property of homogeneous trajectories. Phase trajectories. Homogeneous phase trajectories. And one last comment is, so why did I say that? Well, because if you have time, then crossing may occur, and that's not against uniqueness. Why? Because that means that what you have a time function, and when they cross, it may mean that at a particular value of the function f of t, it goes this way, and at another value of the function time, it goes that way. That's not against uniqueness theory. It may happen. Okay? So that's why I said it makes it too difficult. You know, non-homogeneous time functions make plotting too difficult because you don't have these properties anymore. All right? You are thinking about something like this. Kalsın tozu. Kalsın tozu yapması için tabii ki bu şeylerin değişmesi lazım, simetrik olması lazım ki. Belki versin. Let me ask you. Let me mention another thing. This cross, if they don't cross, you asked a question. You said, so you understand that they may cross if you have a non-homogeneous, non-autonomous system. That's a different story. Because the time function, as I said, may be the implicit driving factor that determines whether it will go this way or this way, and that can be crossed. So that's one property. The other property, the other remark is, what happens if you have a third order system? X, Y, Z. She asked that question, and I said, but how do you plot it? And I said, you plot it pairwise, right? Y versus X, Y versus Z. And again, when you do it like that, when you plot an nth order system pairwise, the trajectories that we have are not the exact true trajectory. They are not the exact pictures. Do you see? What are they? They are sort of like projections. Do you agree? Because X, Y, and Z covary, they change in 3 dimensions. They kind of go like this, right? Okay? Do you agree? Let's just imagine this. X, Y, and Z, right? And then something like this, and they kind of go like this, right? Let us say. And without ever crossing, you can just visualize in 3 dimensions. Without ever crossing, the trajectory may go like this, right? Now if you project this, if you examine this on an XY plane, how XY moves, you will see that it may look like it's crossing. Do you visualize it? Because if you take, if I just look at my hand, if I do this without ever crossing, it's a kind of do some sort of like a butterfly shape, okay? And never crosses in 3-dimensional. If you look at it, it will look like this, right? Whereas in 3-dimensional, it's not crossing. You understand? It's a simple example. So what I'm saying is, in 2 dimensions, and if you take an n higher than 2-dimensional system, and if you do pairwise plot, 2-dimensional plot, it will look like these projections look like they cross, and the projections will cross, but that doesn't mean that true trajectories cross. So keep that in mind. So you are getting these projections there. The 2-dimensional crosses give you an idea about the shape of motions, but they are missing pieces of it. You are missing dimensions. So you don't have the complete information.
Hocam, determinist olmayan sistemlerde bu kural geçerli mi peki?
Stokastik sistemlerde değil, hayır. Stokastik sistemlerde yine trajektörünü çizebilirsin ama cross edebilirsin trajektörünü. Bu trajektöriler nth order sistemin another research was computer oriented olan için another research project. Bu trajektörileri belki en güzel, en useful, nasıl işte projectionlarımı sabit tutarak mı, değişik katlarla nasıl sunabilirsek, diyelim ki çok başımıza gelen bir şey mi? 5. ortada bir sistem dynamics modelimiz var. Şimdi trajektörileri incelemek istiyoruz. Bu information'ları nasıl, bu phase information'ı nasıl present edebiliriz ki kullanıcıya? Sistemin dinamiği hakkında en nispeten en clear bilgi versin. En açık bilgi versin. Bu da açık değil çünkü. Şu anda yapılan sistem şu. İkişer çiziyoruz. İşte o ikişer çizdiğinde sana o projection'ları veriyor. Oradan da işte bir fikir arıyorsun. Bu da enteresan bir sorudur. Bunun incelenmesi de enteresan. Ya böyle zor bir şey. Ha?
İleriyle projeye.
Yok işte istesen proje yaparsın. İstesen bunları yaparsın. Ha? Hocam her şey yapılabilir her level'da. Yani bir şeyi bir level'da yapın, proje level'da yapınca daha az yaparsın. 3 haftalık bir iştir. Öbürü tez, 6 aylık, 9 aylık iştir, doktora tezi, 3 yıllık iştir filan yani. O yüzden kendi bir level. Okay, let's write down the rules then. Okay? The rules, so in general we can write down the procedure. So general steps involved. Siz bunları mı, böyle mi, Facebook gördünüz mü bu derste?
Böyle anlatın. Evet.
Nasıl anlatın? Başka türlü anlatıyor belki de aynı şey oluyor. Özünden mi oldu?
Yani mesela saldırı bakmak için çok önemli bir sistem buluyoruz yani. Kendi çok zordur. Ama yani x versus dx dt çizgisi önemli.
Tabii o da yapılabilir. Yani renklerin de hareketini yapılabilir.
Ya da renklerin de
O da yapılabilir. Ama en tepeyi budur şeyde. Yani bu optimization tabii amaçlı başka olabilir. Optimization amaçlı, çünkü analiz amaçlı. So general steps involved. 1. Find the equilibrium point. These are things we already know. 2. Determine their stability. And here we have 2 cases. A, linear. B, after nonlinear after linearization. We haven't seen this one yet. The example. Third one is because this is linear, right? So the only example we saw was linear. Third one, yeah, I mean after. It's not that we haven't seen this. You know how to do it, but you have to apply it. Obviously, you know it because you have seen an example of what Taylor series linearization of a second order system. So you just take the second order system and you do Taylor, you didn't remember Taylor. So you just do your Taylor series linearization for a two variable system. The third one is isoclines. Find right phase equations. The x1 over the x2, whatever two variables you are using, and determine isocline equations. The isocline equations are what? dx1 over dx2 equals 0, dx1 over dx2 equals infinity, or goes to infinity, and what else? dx1 over dx2 equals plus or minus k, if you want more. Plus or minus k being what? Plus 1 minus 1 plus 2 minus 2. So 3, 4. That 4 is this step. Determine the field arrows, field or direction arrows, and plot a trajectory. These are the steps involved in phase plane construction and phase plane analysis. dy over dx, dx over dt equals minus 2x, dy over dt, and making the examples get simpler and simpler. These are the equations. Quickly, what are the equilibrium points? Huh? Two. Stability. Yeah, you can do very sophisticated work, find the eigenvalues, write the A matrix, right? Write the A matrix, find the eigenvalues. Don't do this sort of thing in the exam. If you in the exam, if you look at something, first take just 15 seconds and look at something and see if there is a what? A meaningful, practical, clever way of doing it. Okay? Don't take an obvious equation and spend 5 minutes, writing the matrices, and I could give you a fifth order system which is perfectly diagonal, and if you write down the A matrix, write all the equations and all that, it might take 5 minutes, and then whereas by looking at it in 5 seconds you can write down what? Diagonal. So be careful, whenever you see something simple, do it. So what are the eigenvalues here? Sözünüzü yazmayın. Tabii, direkt negatifdir, sonucu yazıdır, olabilir. Ben eigenvalue'yu sormuyorsam, ne soruyorsam onu yazın. So what's that? Therefore, asymptotically stable, right? Asymptotically stable. 3 dx or dy over dx and dy over dx. Your dx equals what? Y over 2x. So from here, dy over dx equals 0 on y equals 0, dy over dx approaches infinity on x equals 0. Right? So let's finish. Here is the conclusion. Y, X, equilibrium point. What else? What are the isoclines? Let's see, it's really easy. One of them is y equals 0, the other one is x equals 0, right? So I'm not going to redo this because I have to do, right? Let's see, on y equals 0, which one? This is y equals 0. The isoclines are what? 0. So what are they? Huh? So it's kind of like this, right?
Yes.
Yeah, you got tangent. Yeah, it cannot, so this means it cannot cross this axis. That's what it means. So the other one is this. Alright. And then in between, this is easy, right? They define quadrants. Right? In this quadrant, what does H do? In this quadrant. If you're in this quadrant, what do you do? Or here, let us say. Here. So the X goes down, and also Y goes down too. If you are here, this fairly simple. If you are here, what happens? X what? X goes up, whereas Y still goes down. Do you agree? Look at the equation. If you are here, huh? Y goes up, X. X goes down. Yeah, oh yeah, you're right. I thought you were saying, I'm thinking, I wasn't listening to you yet. X goes down, yeah. That's correct. And here, this is the, okay, this is the picture. These are the field arrows. So now, if you start here, what does it do? It doesn't have too many, not too much action space, right? Not too many places to go. Where will it go? Huh? Yeah, it cannot violate these, it cannot cross this, it cannot cross this. So where will it go? It will just go like this. This is it, right? And the point is, what was the point again? The point is asymptotically stable. Okay? So I'm not exactly connecting it to it, I'm correct, because to show the fact that it will take a very long time to reach, infinite time actually, to reach the point it's that asymptotically stable. What happens if you start here? Right? So this is no big deal, this is easy. Alright? That's the behavior. And if you want to be more precise, the behavior, I'll tell you something. These are around the equilibrium points. Now let me come back here. What if I start, and it was hard for me to do, but what if I start at a point which is not near the equilibrium point? This is not near the equilibrium point. Will all the principles and rules results apply? Why? Because it's all kind of system. And it's unstable, not unstable. No, that's not the reason. This is, it's globally, whatever property I found, which is what? Unstable, and the type of instability is what? Growing oscillation. That property is a global property of the system, not a property of the what? Of the equilibrium point. So even if it's here, you have this. I want to do it because that will give me a hard time. Do you see? The same thing would apply. You understand? Now, because a linear system. In a linear system, I cannot do this. I can only do this. and I will stop, and here I have a question mark in a nonlinear system, because I don't know when I'm far away. Here, it's linear, and again the property is global. Global it's asymptotically filled. So what happens if I start here? It will still go down to this one. Now the only question is, will it come down in a straight line? Sometimes you wonder about these properties. Or will it go like this, or will it go like this? Well, this way, if I'm correct, it goes like this. So it's sort of like, the flower shape is sort of like this. It's not straight line. The reason being, well, one way of finding is what? Is by finding more isoclines. Do you agree? If you find more isoclines, you can figure it out. The other way is just by looking at these coefficients, which one will go down faster, which one will go down slower. You know, when you have equal y and x values, minus 2x minus y, so you can tell that, you know, x goes down, for equal values, x goes down what? Faster than y. That's another way of thinking. The other way is d squared y over dt. Sometimes this works too. No, d squared y over dx squared, not y. D squared y over dx squared equals, what do I get? It's minus y over 4x squared from here. Okay. Is this correct? Huh? And in this region, if you analyze in this region, this is negative for x, y positive, which means that you know, when x, y positive, if this is like that, that means they should have this type of shape. Okay, you know, so kind of look at the concavity. So that the conclusion is this, and you can do the same things over here. Here it's like this, and then here it's like this. This is a little bit detailed information. As I said, this information you can find. What I'm saying is this: none of these, all these must obey this step, right? They must obey the isoclines, but the fine detailed information is the fact that what? They could come straight, right? Or they could come this way, right? That's the detailed information. This, as it turns out, this one has this type of shape. Okay, so these are the phase trajectories. One more piece of information. What happens if you start on the axis? What happens if you start on the axis? Huh? Is there something special about the axis? Yeah, the axes are special. If you start on this axis, what do you do? Huh? Yeah. To obey these arrows and obey the isocline, you go like, there's no other way. And this one goes like. And you can check it out. If you have y is 0, y doesn't change. If y is 0, y doesn't change, but x goes down. All right. Okay, let me show you. I'll show you another example. So this is still linear. Let me show you a quick, at least a partial nonlinear one. We'll do full analysis later. So here is another one. Finally, nonlinear. A nonlinear predator-prey interaction model. to an ecological model, what's a predator and what's a prey? Huh? Which one is avcı? This is tiger, and this one is what? Deer. Huh? Huh? What? This is deer. This is tiger. This is human. No, this is human. This is the rest of the world. Yeah. Okay. Or this is human. This is human. That only happens in what? Only the human being. No, only human beings. You see, animals fight with each other if you analyze nature, but that's very, very rare.
Aslan dişinin daha önceki çocuklarını öldürüyor. Sonra onu kendi çocuklarını öldürüyor.
Yeah.
Sonra gidiyor. Sonra başka bir aslan gidip onları öldürüyor. Ve kaybediyor. Çocuk öldürüyor aslanlar.
But usually, doğru, o var, o nadiren var. Ama o family düzeyinde ve individual olarak var. Fakat genel olarak hayvanların arasındaki sosyal anlamda toplu savaş ve kovalama, şeyden yok etme, şeyden öldürme filan genellikle hayvan türleri arasındadır. Öbürleri şey yaparlar yani, aynı türden olan hayvanlar değişik bölgelerde ve değişik şeylerde otururlar. Bizim species şey var yani. Evet. Neyse, şimdi bu tiger, deer veya shark, small fish, big fish, small fish. Okay. Now, there are all sorts of interesting models. We are not going to discuss in this course. The course is not about model building. That would be, this was I-550. You spent 45 minutes building this model. You know, what kind of causal relations, what kind of positive causality, negative causality, so forth. I will just give you the result based on this assumption. Assuming that by itself, prey population grows indefinitely. By itself, this is typical. Approximately, you can say typical. By itself, prey population will grow indefinitely. And by itself, predator population would decay. Would decay indefinitely. This is not that stupid. You see what I mean? In other words, if you left alone, these little animals, little fish, would just keep on prospering. What controls them is the predator population. They get all sorts of food, you know, happy life, so forth. By itself, the poor predator population, you know, you sometimes feel poor for what? For these little animals, rabbits especially, right? Rat runs and these cats, whatever. Different types of wild cats, right? Some sort of cat will chase the rabbit on the wildlife channel, right? And you feel sorry for the rabbit, but usually, you know, the cat is in trouble because the cat is hungry, hard to find food. So the cat population, the hunter population, will usually go to zero without prey population. So if you put all together, here's a model that looks like this. A simple model looks like this. Dx over dt equals x is, this is x. Prey population is x. The prey population is x. Predator population is y. Dx over dt equals lambda x minus beta xy. dy over dt equals minus gamma y plus delta xy. Alright? Alpha, beta, gamma, delta, or positive. Do you agree that that's true? That this model agrees with these statements? Huh? If you Without prey, without predators, prey population grows indefinitely. Without prey, predator population goes to zero. So that works. When they interact, predator population is harmed by the interaction. They are being eaten. When they interact, prey population benefits from the interaction because they eat. Okay? The two are not equal, as you know very well from system dynamics. Why? Because when they eat, they kill these animals, but the eating action is not a flow from what? From rabbits to tigers. That would be utterly stupid, of course. Okay? That's not the direction. That's why they are not eating. Right? You don't eat and become a what? Another tiger. So it's just a positive. Just they both, this decreases, this increases, but they are not the same term. Alright, so this model passes the fundamental basic selection test for validity, but beyond that it has many weaknesses. That's not the purpose of this course. So this is a very famous model that ecologists use, mathematical ecologists use. Alright, let's just quickly analyze. Step one is what? Equilibrium point. What are the equilibrium points? We will not finish this, but we will quickly do a good part of it in just 10 minutes and then we will stop. What is it? Equilibrium points. What are they? How did you find? You have what? L, right? No. And the other one is what? Well, you can factor out what? From here, what do you get? From here, what are the possibilities? If you factor out x, what do you get? Huh? X equilibrium 0 or y equilibrium alpha over b, baseline, right? From here, what do you get? Y equals 0 or x equals, is this correct? Correct? Huh? These are, so the equilibrium point, if you put all together, if x is 0 in the first one, in the second one, y has to be what? 0. So here are the equilibrium points. If you put everything that way, the equilibrium points are 0, 0, and what? X, this is x, this is x. The first one is x, the second one is y. And you cannot say it, right? Gamma over delta, alpha over beta. Alright, so these are the equilibrium points. Yeah. This is Greek torture. A nationalistic interpretation, right? The Greeks' revenge on Turks. Okay? Alright. What's the second step? So you have two equilibrium points. Non-linear system, more interesting finally, right? Two equilibrium points. What's the second step? Huh? Stability of 0, 0 and stability. Linearize. What are the functions? What are the functions? The functions are, look, f1, xy is what? Right? Do you agree? And g, or f2, sorry, f2 of xy is equal to what? So now what do? To find the Jacobian, I take all the partial derivatives. Partial of f1 with respect to x equals alpha minus, then the second one is partial of f1 with respect to y equals minus delta x. Partial of f2 with respect to x dt is approximately equal to x minus 0 times 0, just the other way around. Y minus 0 times minus gamma, which is equal to minus gamma y. I linearize it, right? What's your conclusion? Quick. We are going to write the A matrix, find the eigenvalues. No. What are the eigenvalues? Lambda 1 equals this, lambda 2 equals. Therefore, quick, unstable. 0, 0, unstable. 2 around. What's the other one? Around. What are the points? Gamma over delta, gamma, alpha over beta. Right?
And I will do this when I stop.
This is a little exercise for you anyway, for what? For linearization. This is okay. So what are what's this one then? Dx over dt is approximately equal to linearized is equal to what? X minus times 0. You obtain 0 there. Y minus alpha over beta times, when you put this in G, that is G, in F2, oh yeah, in here, yeah. No, I mean this one, I was checking this one. This one yields 0, right? Huh? That's correct, yeah. So the other one here, you're right. That one doesn't yield 0. That one will yield what? Minus beta times dx value. Which gives you this? Minus beta gamma over delta times y minus this. Keep that. dy over dt is approximately equal to this time x minus that times this time just the other way around. What is it? This one. Delta over alpha over beta plus y minus alpha over beta times 0. So it's kind of symmetrical, right? And this time we get this. Delta alpha gamma over beta. No. It's not gamma, this is alpha, right? Alpha move. Alpha mı? Bir dakika ben bir şey söyledim. X minus. Tamam mı? Neyse bu da mantıklı. Bunu yazarsan nasıl? Şuna Z, şuna U dersen veya Z. Buna Z1, buna da Z2 desene. Ha? Hı? Ne çıkıyor? Ne bileyim ben size yazayım da. Bu ne bu? Ona eğer Z1 dersen veya ona Z2 demen lazım. Şu Z1. Bu Z2 değil mi? Bu Z1. Doğru mu? Yok yazmana gerek yok. Öyle de yapabilirsin. Ama sonuç olarak şöyle bir şey çıkıyor. Doğru mu? dy over dt eşittir. Ne o? Minus. Biraz fazla hızlı analiz yaptığınızı hissettim. Onun için devam ediyorum. Times d2 doğru mu? dy1 over dt, dy2 over dt eşittir. Burada ne? Ha, evet. Bu eşit. Doğru mu? Buraya bakarak söyleyebilir misiniz? Bu kadar basit değil. Tamam mı? Bu kadar basit diyor. Hı? Bunun analizini yapmanız lazım. Bunu yazmanız lazım şeyini.
Ama niye ağlak çıktı yani bir sıfır değil de tam tersi ama yine ayrımcılar o onu dönüştürdüğü için yani upper triangle değil lower triangle.
Tamam ama sonuç ne çıkıyor?
Yani bir pozitif bir negatif iki yıl çıkıyor.
Evet.
Aslında bazıları pozitif yıl olduğu için onu söylüyor.
Benden niye de çıkmıyor acaba? Çünkü zihninden fazla hızlı çözüyorsun diyorum. Dediğim bu. Öyle kafandan bir approximation yapıyorsan ama çalışmıyor approximation. Ya da benim yaptığım yanlış. Denesene onu yapsana. Bunun eigen value'su çıkmıyor mu? Eigen value equation çıkmıyor mu koyarsın?
Yok onlar upper triangle'ın şeyinde lower triangle aynı.
Tabii öbürü tersi değil de, simetri değil. Burada lambda 1, 2 eşittir, artı, eksi, I, kontrol edin bakayım, şöyle çıkıyor. Square of. Böyle çıkıyor mu? Böyle çıkıyorsa farklı sonucu alıyoruz. Ne çıkıyor bu? Borderline stable. Hayır. Yok öyle bir şey. Şu anda yeni bir şey geldi. Aynen. Hiç öyle bir şey demedim ben. Hayır hiç öyle bir şey demedim.
Ama yanında weak result olduğunu söyleyebiliriz değil mi? Çünkü
Tabii o ayrı bir konu. Çünkü approximate ediyoruz ve borderline çıktığı için o ayrı bir konu. Ama hiç öyle bir şey demedim. Nereden çıktı? Bizler. Ha? Tabii. 20 dakika sonra burada res var dedim galiba. Testinde biraz aranjman yapıyoruz. Testine